Hello, everyone, and welcome back to the cloud and streaming stage. In the next presentation, we will be hearing from Flo Pachinger, who is a developer advocate at Cisco Systems, and he will be talking to us about how to detect malware in encrypted traffic without encryption. So this is a very interesting presentation that I'm sure we will learn lots from, Flo. So over to you to give us the rundown.
Perfect. Thank you, Jonas. And hey, everybody. It's really nice to meet you and to be here, of course. I am Flo Pachinger. I will talk a bit about how to detect malware in encrypted traffic without decryption. And yeah, I would say let's get to it. I would like to put the TLDR in front of it, and it says so encryption is good for privacy, of course, like we can encrypt it, but however, it gives challenges to other aspects of security. So how do we know it is like the encrypted content or the data, the payload is malicious? And like the short answer is contextual flow data is here to help. And this is kind of the TLDR, which we will go into this session here. So what do I have prepared for now for you today? So first of all, I would like to recap a bit, and this is very important because we're talking here about also like a machine learning model, like in towards the end, is like how does encryption work again? So I would like to go more into this detail. And then for some of you, it may be a recap, but I think this doesn't hurt. Then I would like to talk more about encryption and malware, like are they BFFs, and what about the current encryption trends, what we have right now. And then we go directly into how actually, and this is coming more to machine learning and to data science, how do you decide which encrypted traffic is benign and malicious? And so we'd like to say, okay, like which is good, which is bad. And of course, I will explain some of the magic what is happening, and you can try it out yourself, of course. So just a bit on my persona, so that you know, okay, who is talking right now here? So like I am Flo Pachinger. I'm talking right now here. I'm from Vienna, Austria. And I'm a developer advocate at Cisco, where I focus mostly on IoT and then also, of course, on machine learning and data engineering. So, like, if you want like to know more about my products or like my projects, what you see here, just go ahead, like on Twitter or on GitHub. Like all the code is available there, and of course, if you have any of the code is available like on developercisco.com. All right. So like now I would like to say, hey, let's go to okay, how does this encryption work again? And here, this is a really basic example, but I think it's a definitely a good start. And if you are not familiar with it, like I'm happy to basically explain the basics there. So we have Alice here, a classic Alice Bob example. So A, B, and Alice would like to send the message. And let me just give you my laser pointer. So Alice would like to say, hello, Bob, and would like to send it to Bob, but of course encrypted. Like she doesn't want to know the whole world, like sending the via the internet, for example, and say, hey, I would like to know that I'm greeting or like the message what I would like to send to Bob. So Alice is basically encrypting it with Bob's public key. So I'm not going super more into detail into public private key, but like basically Alice has a public and a private keys, and so does Bob. And if Alice is encrypting this message with Bob's public key, it would look like this. So basically, it's encrypted. It's not the same as "Hello Bob," like a normal string, what we can see here, but like this message here, and it will be sent to Bob. And Bob knows because since like Bob knows his public key, there is a equivalent, or like it's not the same, but it's like a private key which basically can work with the public key. So what does it do? It says here, all right, I would like to encrypt this message. Bob's using his private key, and by the way, Bob's only like the private key is only visible to Bob. Like Bob is not sharing his private key. Bob is of course sharing the public key, but not the private one. And so Bob is decrypting this message, and it can do that because with the private key, he can decrypt it. And he sees, hey, oh, Alice wrote me hello, Bob. And so does it say like vice versa. It goes the same. So like if Bob is sending something to Alice, Bob is using then Alice publicly to encrypt the message, sending it to Alice, and Alice is, because she only has her private key, and decrypting this message from Bob. And this is kind of like a classic 101 example, right? What you can see here, but this is also used in HTTPS. So as we're doing right now, when you went to the Big Data Conference website, right? There you see HTTPS, most probably using TLS 1.2 or 1.3. But this is actually what happens, like a classic TLS handshake, in order to encrypt the data, what is being sent over the internet. So what do we have here, and what did your client send? Like you're sitting now in the laptop there, and your client is actually saying, apart of course the whole DNS process, what I will explain later, but is requesting data from the Big Data Conference server. What does the client do? Like the client needs to establish some some communication in order to say that this is only like the goal is here that the client on the left side and the server on the right side are exchanging a shared secret, and both of them know the shared secret, but nobody else. So when we have the client here, the client is saying, like your laptop is saying, to or giving the server a hello client message, and it gives a list of the preferred cipher suites. So which means kind of, okay, what kind of algorithm or what kind of encryption algorithm are we using? I'm supporting this cipher suite, and please select one of these. The server is getting it, selecting the cipher suites, creating like the whole key share, so like public private key, puts it like, of course, like there's a certification there, like server certification, and then sends it back to the client with a server hello. Client now, again, they have now a specific key share. So as you know, like as we did with Alice and Bob before, and then sends the finished message there. So finished means, hey, I am the client, like this is all secure. I know that who you are. Like we have the same secret, it's fine. Server sends again back, and then the data can be requested. So all of this happens actually before any data is like your client will receive from the server. So this is all of it. What is happening here? All right. So with this is TLS 1.2. So like HTTPS is using TLS as a subset. So you in the browser, you're actually using this technology there. Then with TLS 1.3, you gain more performance and more security. So how does it do that? Like performance-wise, you can see definitely like, hey, there is one big thing is they're missing. So here you can see that actually the client is doing the same, like client hello, and actually says, hey, this is a list of the preferred cipher suites, and they are definitely more secure, like starting from TLS 1.3. And the client is also initiating or sending also the key share to the server. Then the server is selecting the cipher suite, doing this key share, the certification, and it's finished. And in one wish, basically, in one part is like the client is sending the finished message there and can already request the data. So you can see here a lot that it is more secure, like the performance. You can see like on lots of data, the performance is definitely better with TLS 1.3. But then again, security is also higher because of how they're sharing the key share, and also on the supported cipher suites on this part. All right, so like this is classic example. So like I think like TLS will be even more and more important in the future, especially 1.3. But basically it comes down to this, what you see here, so that we have like a public and a private key. We are encrypting the traffic. This is not visible, like, or basically like the encrypted part is visible to the internet, or can be visible to the internet, to the whole internet, but the decryption encryption is happening here on Ali's side and on Bob's side. And this is the classic part. So why I'm saying this, right? Like, because like going more into detail and how to and like analyze the traffic, it's important like to understand these basics there. And now let's start with the one of the challenges there. So for example, with TLS 1.3, there are challenges like man-in-the-middle decryption. So what does it mean? So on the first part, you can see here, like we have a common name, or the server has a common name and subject alternative names. So what does it mean? Like I'm going back here and saying, so like if Alice is requesting something from Bob and Bob is sending it back, and Bob in a way is the server, then Bob actually, Bob actually gives Alice a common name and maybe also subject alternative names, but of course already encrypted. Because if you go back here, if the server is sending something back, this is already server side. Like the content on the server side is already encrypted. However, on the client, like if the client, like the very first message, when the client is sending something, this is not encrypted. Like how can it be encrypted? Because in a way, if the server doesn't know the client yet, right? So here we say here comes into play like the server name indication. So basically, server name indication is that the client is sending to the server, but this is done uncrypted. So this is done uncrypted, and which means also the SNI can be spoofed, right? So for example, like when we bypassing, how can we bypass a decrypting device? We can basically say or like send a fake SNI name. So this is right in the beginning, right before even the very first beginning when the client is communicating to the server. So for example, we send a request to website A, which is basically not allowed, but we are actually indicating like actually in the SNI we are saying so like we are requesting the website A, but sending actually the SNI name and the request to website B. So what's the cool part? Like you can actually go to the website A, right? Because we create a fake name saying, hey, actually we are going to this server, but actually we are requesting, like in the request, we are actually requesting it to the other one. And what are the reasons for that? Like, why would you do this, right? Like, why would you fake it and say, hey, we're going that? No, actually, we're going the other direction. So classic example is, hey, there are forbidden websites, right? But yeah, that's some boring stuff there. But of course, malware. So malware can actually connect to a command and control server. And through that, they're saying, hey, actually, no, I'm not going to facebook.com server. Actually, I'm going to my fake facebook.com server, for example. So this is some stuff what can be happening with SNI. So what are the like what is the goal of it, or like what can be used there? So there are some like new encryption protocols or like there. So like just for you to understand is that we have like here like TLS 1.3, which is highly adopted, of course, like already a standard. And adoption is getting more and more. Like TLS, I think, is now used more than 1.2. And we use it for web secure transport. So like HTTPS, they can use it. Our goal is like we have low latency. We have like modern crypto is using like really like modern algorithms there, and then the privacy, against ISPs. So you can send something, and your internet service provider they don't know what you're sending, right? Because this is encrypted. Then there is DNS over HTTPS, though. So you actually can DNS server, like if you don't know it, like before you are sending, like you're typing in a domain, so google.com, for example, and then before that going to basically google.com to the server, you actually go to a DNS server, you look up what is the IP address of google.com, and then it returns to your machine, to the laptop, and then it goes to the Google server. And DNS requests are usually not encrypted. So you have basically with DNS over HTTPS encrypted request to the DNS server, to the domain lookups. And last but not least is Quick. This is like developed by Google. And interestingly, like when you use Chrome and YouTube, like all these Google services, they are usually like in the Google backend, they are usually using Quick instead of TLS, for example, to have it like to have the web for web secure transport there, right? So here, like they have some specific parts like lower latency and so on, and some advantages there. But I won't go into more detail there as well. But like just focusing on what kind of things, and this is very important for later. So then it will all make sense. Why this is important here. So just a bit for you to know, like with DNS. So here, for example, we are here the user. We would like to request example.com. So we are actually going from DNS to the enterprise DNS server here. And then from there, it goes to the internet service provider DNS. So here we have basically something already filtered. Like here we basically say, hey, we encrypt like DNS is like not encrypted, but we say here in the enterprise server we are already like having the query there filtered by the enterprise IT team, for example. Is it malicious? Is it not malicious? And it goes then to the ISP, and then the same traffic as we did before with TLS will basically happen here with the TLS server name. And with now with secure with DNS over HTTPS is saying here that we are going super secure to the CDN, so like basically to directly to the site without like anybody can basically interfere and know, okay, which website actually am I currently requesting. So everything is encrypted there. Here just some examples with the visibility. So like I hope you get a feeling there that it's everything is getting in a way also more and more encrypted. Just some parameters. So like especially when it comes to DNS, in some cases TLS server name, as you can see here, are getting are clear, which means like they're like visible, they are readable, and by like anyone like from the IT system and so on, like and along the internet. And then of course when it comes to like more server certificates and these kinds of stuff, then this getting more and more encrypted. So this is about encryption. Like, how does it work again? You have a bit feeling there. So this is all building up in order to give you knowledge there in order to explain, okay, why do we things here on these 2 points there? So this is basically the whole understanding there. So now let's go more into encryption and malware. So like we would like to know, hey, okay, like what is bad traffic and so on. So we have encrypted malware traffic. So like we have here on the premise, you're here on the laptop there, and you see like you go on the internet and you type in usually HTTPS, like all of the internet communication, or like not all of them, but like really the majority, most of them is using like a secure and encrypted connectivity. And also you can see it here like on the premise. So like with TLS 1.3, is like it is increasing. So, and this is not bad, of course, because we love encryption, right? Like when you are going on a website, like, and you don't want any hacker or like whatever, or any other government or agencies to know, then of course, why not using encryption there? However, on the downside, of course, content-based matching does not work with TLS 1.3 because everything is encrypted here, right? Of course, you can do here like when you're in a company and you have a firewall and you do some decryption there at the firewall to see, hey, is actually malicious traffic going in? You can do it, but it takes like a lot of resources there as well to do the filtering there, to do the decryption there. So basically when you say, hey, oh, there is something going on, we have some problems there, right? Like, and this is the classic man in the middle problem. So like interfering with the traffic. So should we now basically focus more on the privacy, like legal, like for example, when it comes to government, like they want to know what their users and their citizens are doing, versus hey, actually, also malware can go through this tunnel. How can we basically protect our laptop, our systems there? So we have here, of course, some discrepancies there, which we are trying to solve now. So first of all, what we said there is that privacy is a benefit against ISP and the local government. So what you see here is that when everything is encrypted, perfect, like in a way that you can't see like what users are doing or what the content is. Of course, this doesn't resolve around like the threats against data privacy, because here, like, just to be clear on that, is like you have an encryption from one end to another, but what the server is doing with your data or with the data on the other side, this is again something what we are not covering here. So like here is basically about, this is the communication privacy between you or like the system or the local area network, what you're here, and to another server there. And there is also like a really cool read from the NSA, which they're saying, hey, how can we deal with it with encryption, like to give you a good and secure content filter. So like talking right now, of course, on enterprise networks, like on company networks there, versus not using any encryption at all. So there is some really cool guidance there, like a document which I definitely would recommend you to read, where you say, okay, how can we basically balance this act there. And we will come to this later on in a bit. So like I'm going now more to focusing on what kind of malware there is, especially how they're doing it, and then you will understand like in the next point, actually in the next larger point, okay, why I'm going through this. So what right now what can be done is that if you have a malware on your smartphone, for example, and you are actually would like to access example.com, the domain. And usually lots of this content on the website are on the same CDN network, right? So it's like a content delivery network there. And what you see here is that that when your smartphone is doing the same DNS query, example.com, perfect, it says, okay, go to the CDN. Then we say, hey, server name, example.com, go to the CDN, and server certificate, you will get the same back. Everything is TLS, it's perfect. But when you start then to actually get and send data to the, and you would like to do this on an example of con, of course, but via this malware, it actually sends not to the host example.com on the same CDN, but it actually sends you on malware.com on the same CDN. And this is called domain fronting. So you actually think that you are going to the same CDN and this is actually the server, but like inside this CDN content delivery network there, you are actually going to malware.com. Of course, you can supposedly you have a malware there inside of your smartphone, of course, or your computer. But the most important part is that like domain fronting is of course against the standard, the HTTP standard. Like the host should be the same as we queried it. And of course, usually AWS and so on, like they forbid this specific domain fronting there. Another thing is as well, what I would like you to remember is definitely that malwares are continuing to shift to TLS. So you can see here that like starting from about around 2 years ago, that the curve is getting more and more, and you can see like the trend is going more and more that malware using 1.3 capable clients are going up more. So excuse me. So like when you see here, like you can definitely see the trend going up that like malware is doing more and more TLS, which is of course like for us now is getting a problem there. And finally, when you go to malware domain faking, this is also a classic part where you actually have a malware installed, and actually the server name you want to go to is like classic with like such as Amazon, Google.com, Twitter, whatever, but it actually goes to a malicious IP address. So you can see here that like on the directly on the client, like you think the user is going to this website, they can spoof it, and then in the end you can see, hey, or the user believes this is actually the true Amazon page or the true login page, and then the malicious server is getting the user's credentials there. All right. So now I hope I didn't bore you too much with that, since it's like I know a big data conference, but this is, as you know, it's very important to get some understanding on why using this data, on how to on what are the problems there are. So you definitely need some domain specific knowledge there, which I hope I provided to you now. That basically encryption is increasing, malware using encryption is increasing. And so now how can we basically, because we don't want to decrypt any traffic, how can we help? Like how can we help a user to see, okay, what is a malware and what is not a malware? And this is what I would like to talk in this point now. Basic example, how do you decide which encrypted traffic is benign and which is malicious? And first of all, so yeah, this is not on my, so unfortunately, but like this is not on this is not my work, but like on two of my colleagues there, Blake and David. So they did a lot in the security aspect there, and they did all the research and all this whole project there, which is, and they also wrote some papers there, such as identifying encrypted malware traffic with contextual flow data. So basically, just give you like I definitely recommend you to read this one, and I will there will be links on the last slide. You can find this on Google Scholar, like this is public knowledge there. But they say basically, hey, we are actually not decrypting any data. We are analyzing the metadata. And here they are saying here like data omnia approach, they state this here. Like this is just to highlight this one here. So they say, hey, we are using a lot of data from the client, but we are using also data from the destination. And this is more coming in their second paper, which is also, and if you want to scan it right now and read it like in a way, or like just to have a peek, it's like just scan this QR code there. So they are also setting in this paper, which is also related. They're saying, okay, like how can we use like TLS fingerprinting and using destination context and other knowledge bases there in order to analyze, okay, is this traffic actually problematic or like malicious or not? And for that is one thing, like if we only look at TLS fingerprinting, so one thing is we only look at TLS fingerprinting, this might not be enough. And I will come in 2 slides later on this. One thing I would also, before going into this one, is that they open source their tool where they basically collected all the data, and you can find this on this GitHub repo. So this is called Project Mercury. It's an open source tool written in C++ mainly. And they are basically extracting all the data from a super network level, like we are talking about here, layer 2, layer 3, 4, like all of these, and to get the metadata basically out of the traffic there. And you can use it, like feel free to use it, of course, because you can get the traffic, you can lots of data there, and I will show you as well like how they used this tool here. First of all, I would like to first saying, okay, like I think this is understandable. So like we are using like the client data. So like TLS. So like the client is sending, like when we going back, and I would like to go back to this one because this is important so that you know more about this. Is that you see here that the client is sending something, a client hello, to the server hello. So this is the first initialized call, right? Like the client hello. And very interestingly, with this client hello, you can already like know some information on the client, like what kind of like operating system maybe, what kind of software is the client using. So you see this already here. So let me just go back shortly to the next slide there, because this is, for example, this is an example of a TLS client hello. So what kind of data? So this is kind of like a data hunt now, right? So you can see here that the TLS version we are having, the length of it. You can see what kind of cipher suits are supported, and be aware, like these cipher suits, they are different from operating system. They are different from the browser, of course. Like Firefox is using different cipher suits than Chrome and so on. So you can see here, like they're all different parameters there. However, the thing is that most of the operating systems, or like especially, or like when you look at Windows, for example, they are using for all of the applications the same S channels on TLS. So the fingerprinting is kind of tricky. So, for example, Office is having the same S channel, Internet Explorer, WebEx, and also, of course, Malware could use the same S channel there, right? So this is now the tricky example. Like, how do you do this? And this is why they are saying, hey, we need to put the destination context as well in there. So right now, what they're saying, hey, we should like, and this is the input there, and this is the whole machine learning output there, and what they would like to do is we are saying, hey, we are getting the fingerprint string from the client hello packet, what you just saw. Then, of course, source IP address from the client and the port. But they are then also collecting, like this is all the inputs for the machine learning model. Then they're using the destination context, which means they're saying we would like to know where this package is going, like with the destination IP address, which is visible. This is not encrypted, of course. And then, of course, the destination port plus the server name. And this is done with the SNI. So this is also unencrypted. Like TLS SNI, as I talked before, this is the very first call. The server is sending the encrypted, common name, or like the certificate name back, but the client is sending it to the server. This is the very first call, unencrypted. What do we would like to get out of there, right? Like there are three outputs they defined, which is they would like to define what is the client process name. So is it using Firefox? Is it using Chrome? Is the destination coming from Word? Whatever software. Then they would like, hey, is this a malware? Like I would like to detect, hey, is this a malware there? And then the operating system name. So this is they would like to input saying, hey, this is the input there, and this is the output. What the inference of this machine learning model would like to put out there. All right, so like just for you a bit like to recap is like the TLS client hello. We talked about this. So like this is basically the first slide what I talked about. And here we have in this initial data package here, this is the client hello. And it says here like what are the offered cipher suits, what are the extensions. So like I just showed before. And usually we can already say, hey, like if we have like algorithms which is super more secure, like more browsers are using it, and like on the laptop or on desktops, and mobile applications prefer more efficient encryption. So we can already know about the cipher suits. Hey, this is could be like most probably a mobile device, or this is most probably a laptop. Then they would like also like this is why future like they didn't put it in the Mercury program yet. However, they also said, okay, what is the sequence of the packets and the length and the time? Because they say, hey, there's a malware behavior which can communicate with the command and control server. It's it needs time to write to the disk and so on. So like we are talking about milliseconds, like in that time span, right? Or is it a classic network behavior where you have a sequence of packet lengths, you have a specific, or like usually can be random, but like usually like a specific time interval between the packets there. So you need to look at the lengths and the times there and to see, okay, how is actually malware behavior and how is the network behavior. All right, so like with that good ground, I hope we are going to the final one, which is basically how this the magic happens, and especially I think like I would ask this question, where do they get the data? Because of course, if you have a nice model, but like where do they get the data? So let me explain some of the magic there. So I think most of you know about this. Machine learning, you can use unsupervised machine learning, supervised machine learning, and then in the end to use specific techniques in order to predict something. So in theory, this is more talking about in machine learning is you get in the label data, you train it, and then you have the classifier out of it. Like you basically create a model for inference. And then last but not least, you say, hey, you have a classifier, you have the data, you do the inference, and then you have the results. And these results are, what I said before, is it like, what kind of operating system is it? What kind of a process is it? And then again, what is it? Is it malicious there? And this is what they did. So they put the labels, the data, did some data cleaning, did some training, and then basically have the inference there available. And then with the results, they are feeding them back, of course, into the whole process there and iterate it again. All right, so the knowledge bases. So like, where is the data coming from? And that's the cool part, because like working at Cisco, there is some really cool tools out there, especially in the security area, where they can get the data from. So they tried in their own network. So like they installed like in their own network, the AnyConnect client. So some of you might know it. This is like a software piece from Cisco, usually where you can connect to VPN. But they have also network visibility module there. And with that, they actually are getting these data from their hosts. So they set up some machines there, different operating systems. They put on every one of them an AnyConnect client there with the NVM module, and they get the data out of it. They get the network 5 tuple out of it. So they say source IP address, source port, destination IP address, destination port, transport protocol. They get the event start timestamp, name of the communicating process there, then the SEH 256 hash of the process executable, of course, and then the host operating system. So these are the data points. Plus, also, because that's the cool part, again, to have access to these tools, they have access to the Cisco Threat Grid Sandbox. And this is actually a sandbox which is sitting in the cloud and which is having like a sandbox environment, let's say a sandbox virtual machine, like only one virtual machine, which is then executing specific applications or executing or opening specific PDF documents, anything. How does it do this? Is like Cisco is also like having firewalls. And if a firewall is like, if a PDF document, a malicious one, for example, is going through the specific firewalls, there is a setting where you can basically automatically upload this PDF document. The firewall doesn't know if it's malicious or not, uploading it to the specific cloud. In this specific cloud, in this specific threat grid sandbox, there it will be executed or will be opened. It will be like 10 minutes will pass by and so on, and then it will see like the whole sandbox has all the sensors there. And if the PDF document is installing anything after opening, is getting like requesting some unusual traffic or is doing something, this will be captured in this threat grid sandbox there. So there is like tons of data, and I will show you in a bit like how much data there is. So there is lots of information there. From the sandbox there. So all in all, what you see here is that we get from the client, like from the host, from AnyConnect, we get all of this information. And from the sandbox, we also get all of this information. Like, is this malicious or not? Like, is this specific a program, or is this specific malware? Like, how are they connecting? How is the malware behaving? So this is kind of like getting the data from the specific sandbox, and this is the data what they are getting here. And here we see this is a lot of data. So they get, and starting with the sandbox there, they have like 33 million sessions there in only in port 443, in many other ports there. They have, and this is only the sandbox there. So they gain a lot of data using this sandbox there. But then also on side one, they are like their own, like where they have several workstations here. They also have plenty, like billions of sessions, what you can see from various different points there in order to analyze the data there. And what did they use? So if you're familiar with this, like some of you already know, but like this is like the classic naive Bayes like query in the way, or like equation. So and basically, like in order to know if you're not familiar with that, like I would like to have like a one example there for you, and this is like a question. So like an individual has been described by the neighbor as follows. So Steve is very shy and withdrawn, invariably helpful, but with very little interest in people or in the world of reality. A meek and tidy soul, he has a need for order and structure and a passion for detail. So you might think now, okay, what is he talking now? Like this is just an example to know, and just a game here. When you read this, is Steve, like what do you think? Is he more likely to be a librarian or a farmer? And this is done, or like this is a couple of centuries ago, but like just for you to see, okay, more likely, like what do you think? Like more likely with that, he said, oh, this is actually my more librarian kind of guy, right? Like with that. And this is, by the way, from Kahneman and Tversky. So like just for you to research there. So let's look at not without emotion, but just with data. And you can see here like what are the possibilities, like looking at how many people are librarians on the left side and how many people are farmers. You can see that the majorities actually are farmers. And if you fit the possibility in the evidence there, you can actually see that out of the out of this example, like 40% or out of this naive Bayes equation, you can see like 40% are actually librarians, and there are like when it comes to the farmers, in a way like the 40-20, like 10% are farmers. But in the whole equation, the probability is that the guy, or like the Steve what we just talked about, is most probably a farmer and not a librarian. And this is basically like only 16.7% we thought about it. And this is all like getting in context there. So this is very important to get in context there. And this is why they used a weighted naive Bayes model. Like this is what they used and thought what is the best model there. So they put the two knowledge bases, so the TLS fingerprint there and the destination context, which contains like multiple features there. They put it in there. So they say, hey, this model performed better when we put more weights on the server name, on IP address, and so on. So they, they figured it out there, like they filtered it and they played around with it, of course. And then again, to check, hey, as you said before, what is the client process name? What is the malware verdict? And then what kind of operating system are we using there? And yeah, this is the whole thing, like what we talked before with the, these are the features like from the network traffic there, with the fingerprint, with the TLS fingerprint, with the destination context, and then these are the output parameters there. And what's the outcome, right? So they actually came up with a pretty cool results there. And here, for example, is a confusion matrix with the top 25 processes on the collected data from side one. And you can see here like without a bit of you can see like Microsoft Edge maybe, and then also with PowerPoint, Excel. But usually when it comes to Firefox, Outlook, Safari, to all like these programs, they have a really good predicted there, like a prediction there. So again, here we infer the process name from the TLS fingerprint, like, and the context information, like from the destination, and we actually know, okay, can, without decrypting anything, we know, all right, this is actually coming from Chrome, this is coming from Dropbox, this is coming from like whatever. So we know what kind of process here, like these are the processes on your client, know where they're going, where they come from. So sorry. And then malware detection of results for site 1 and the malware analysis sandbox, they got even with the weighted naive Bayes model a precision from 0.99%, which is in the way really cool. Because if you think about this, this is of course like depending on like the data set was very big. They are also testing it right now, and of course continuing testing this one. But the precision is really good on this one, I would say. All right, so finally, let's go to the conclusion. So conclusion is from my side is that network encryption is increasingly important and increasing prevalent. So it's definitely changing how we ensure the data security on one hand, and then of course we need to change somehow to say, hey, like, is this a malware? Like, how can we detect malware on that? So this, we need to be a good balance on that. And with analyzing just the traffic flow as we did, like with the destination, with the TLS fingerprint, we have a chance there that we can detect the malware and help their users, of course, to have a safe and stay safe there out there in the internet. And of course, there is encryption aware monitoring using machine learning. It enables process identification, it enables malware detection, and it enables compliance assessments. So this is, in my point of view, definitely the way to go. And for example, this is also already here, like within products there. So we in Cisco using this already. So with encrypted visibility engine in the firepower management center, which is basically the management center of a firewall. So to see, hey, we know where, like, if this is a malware or not. And then here you see some examples of, hey, you can see, okay, is it Chromium? Is it coming from Cisco WebEx? Is it coming from Java networking and so on, or from Apple Safari? You can see this here as well. Cool. Yeah, like I promised, last slide. This one is the contextual flow research. So like you can find everything here on Google Scholar, for example, and of course you can find the whole data flow on the whole project with the fingerprinting on GitHub as well. If you have any questions, if I'm really happy, feel free to reach out to me. So like on LinkedIn, on Twitter, on GitHub, whatever there is. I will just leave this slide open just to have the conclusion. And yeah, if you have any questions, feel free to write it down in chat and so on. I think we have still a bit of time to answer some questions there.
Well, unfortunately, Flo, you have spoken well and spoken for a long time, so we're actually a little bit over time. So unfortunately, we won't have time for questions now. But I do encourage everyone to reach out to Flo. He said Twitter, GitHub, and LinkedIn, was it? Yeah. So what's the easiest way to find you?
I would say, yeah, like, I would say Twitter and so on, like, yeah, just for you to see here, like, Flo Pachinger or like Flopach is I think the easiest way. Just reach out to me, and anywhere I'm open to anywhere. That's fine.
Great. I'm sure you've created some questions in the audience here because it was very comprehensive and lots of stuff there for people to think about. Flo Pachinger, thank you so much for presenting to us and putting together a very thorough presentation. You can see lots of effort gone into it. We send you lots of applause from around Europe and in the world, wherever we're sitting. And yeah, all the best with your future journey and all the stuff you're doing at Cisco. And I'm I don't know if I'm feeling safer or more nervous about malware now, but I definitely need to think about encryption. Okay, everyone listening in. So we now have the lunch break. So we'll be back in exactly 55 minutes. So go and get some food, get fueled up, and go for a walk, whatever you do. And we'll see you back then. Thank you.